for introduction. Okay, so in this talk, I'm going to talk about some open source projects at the BOSC. This is Beijing Institute of Open Source Chip. So we know that RISC-V has bring us a new wave in the chip design. And we believe that based on this RISC-V, actually we can envision in the future to build an open source chip ecosystem that can lower the barrier of chip development by saving time to market and the cost of IP, EDA tool, and engineers. So this OSCE consists of several important open source elements, including open ISA and open source IPs, and also open source EDA tools and open verification simulation tools, as well as open source software. Those together to provide reusable open source resources that can save a lot of efforts for chip development. So this is our goal or our envision about the open source chip ecosystem. And the BOSC actually towards this goal in 2021, BOSC was founded by 16 companies. So BOSC's mission is to promote the development of open source chip ecosystem by playing the role of the bridge between the academia and the industry. So, before introducing concrete projects at the BOSC, let me present our perspective on OSCE. For a typical chip design flow, there are 3 levels of openness. The first level is ISA, whether ISA is open or closed. And the second level is whether the design is open or open sourced. And the third level is whether the tools are open sourced. So we know that RISC-V actually made a great contribution on the first level. And while BOSC actually is focusing on the level 2 and the level 3. In last year's RISC-V Summit Europe, and I introduced 3 open source projects. One is the XiangShan open source high performance core, and the second is the One Student, One Chip initiative, and the third is the open source EDA tool, IEDA. And in this talk, I will update the progress of the XiangShan projects, and besides, I will introduce 2 more ongoing projects. One is the open source NOC, network on chip, and another is open verification platform. For the XiangShan projects, many of you may already know that this is released in 2021, and it targets high performance open source RISC-V core. And now the second generation was released 2 years ago, and the third generation, the XiangShan V3, is ongoing, on the way for taping out in this year. As this is an open source project, it becomes one of the most active open source projects of the world on the GitHub. So although it is young, but it grows very fast, and gaining more than 4,000 stars and 600 folks on GitHub. So it's quite active. The XiangShan, there are some highlights of the XiangShan projects. So first is actually this is highly comparable, configurable with Chisel. Actually, we use Chisel to develop XiangShan, and we also has an agile development tool chain. But open source doesn't mean low quality. Actually, XiangShan follows the industry-grade microarchitecture design and the development flow. And now we have formed the 2 tiles of XiangShan core, and the high-performance version is the Kunminghu architecture. This is designed for ultimate performance. Yeah, it's target server and data centers market, and it's supported like RV23 profile, and now the target is the ARM Nervous N2. The classic architecture we call the 9-hole architecture. This is designed for like power air efficiency, and it's targeted like the control and in the industry control market, and the performance is targeting the ARM Cortex-A76. Yeah. And here is the overview of the Kunming-Hu architecture. So it's supported like the vector attention, the hypervisor attention, and we have designed with like the carport front end, and also with large insertion window in the low latency and high bandwidth L3 cache, and also support both the CH and the Tail-link concurrency port. Performance. So we did like RTL simulation emulation for those designs, and the data shows that actually it's achieved our goals. For example, like the 9-hole architecture achieved about like 10 marks, 10 scores for Spark CPU 2006, and the Kunming-Hu architecture achieved about like 15 points per gigahertz. Tape out, and the 9-hole version 2 already taped out last year, and the chip was back and works pretty good. And now in this year there will be 2 tape outs for the 9-hole V3 and the Kunming-Hu V1. So this is a tape out. We also provide the open SoC architecture, so provide some like for example like the IOMMU, like advanced interrupter, and also like TE and like debugger tracing functionalities. And the XiangShan core is also ready for the third-party integration, to integrate with like third-party network on chip. But we also build the open the network on chip projects. This is called Open NOC, and this project is compliant with the ARM CHI protocol, and it supports up to 8x8 mesh network. Here is a demo. Like 16 core connected by the Open NOC are running programs on a Linux platform, on the FPGA. This is on the FPGA platform. So this is the second project. And the third project, I want to introduce the open verification platform. As I mentioned before, XiangShan was developed by Chiso. Chiso is agile is good for agile design, but also raises challenges in verification. So we built a bunch of new tools to form an agile verification platform. And this platform consists of several newly developed tools for like functional verification and performance verification. Besides, we recognize that actually open source can bring new opportunities for public verification, since all source codes can be accessed all over the world. So this is actually common in software engineering. So we come up with this idea that if we can verify the open source project with like public efforts, public open source community. But the challenge is that there are order of magnitude fewer hardware engineers than software engineers. Example, there's a survey about the pull request on GitHub. The Verilog and the system Verilog related PR only accounts for 0.35% in all GitHub. So in contrast, we can see like Python, Java, almost accounts half. So how to deal with this? So we enhanced the verification platform with the following feature. It supports crowdsourcing. It is based on cloud. It's based on cloud, and it supports multiple languages. And more important, we want to involve software engineering to do chip verification. So currently, the platform works, and it is able to support multiple languages for verification, such as like Python, like Java, and C++, and Go. So software engineering can also do verification for chip verification on the platform. For example, here is the Python code for the XiangShan, the branch predicted unit verification and test. And there's the code coverage for the reported by the platform. So those are the projects, open source projects carried on. We are working on those open source projects at BOSC. And there are also some open tutorial sources. You can access those resources online. And we are looking forward collaboration opportunities. So we think like the Linux and the Red Hat model is quite successful for the open source software community. Just as the keynote given by Krista yesterday, commercial success is extremely important for the development of RISC-V community. So we believe that reducing the cost by leveraging the efforts of open source community is beneficial for the development of a RISC-V community. So we hope in the future there will be companies that can provide IPs, design services based on open source RISC-V cores and open source hardware projects. Okay, finally, welcome to the BOSC booth. This is number 7. And we also have some poster during the whole RISC-V Summit Europe. And there's a development zone to demo the SoC designs designed by undergraduates, and that is who are participating in the 101 chip initiative. Thank you very much. Okay.
We want to take some questions. We have time for 1 or 2 questions.
Yeah, I have time for 1 question or 2 questions. So if
All right.
Okay.
Oh, there's one.
Hi, I'm Andrea Bocco from CA. I have a question. Did you try to benchmark yourself with other open source hardware core, like CVA6 core or other core, just to have a clue where you are?
Okay, so the question is, you mean, do we have like a collaboration with other open source core, right?
The question is, did you try to benchmark yourself on area, performance, power consumption with other open source RISC-V core like the CVA6 from ETH Zurich?
Oh, you mean the benchmark cores? Yeah. Well, yes, we actually, XiangShan is a high-performance core, and the CVS and the Popino, those are actually, it's more like the MCU level, so actually they are at two different levels. But I think some tools in those tools are also comparable to those other open source projects.
All right. With that, as we said, 1 or 2 questions. We have time for 1 more question. And I see 1 hand over there. No, microphone is coming. There we go.
Thanks. So, question for this one student, one chip initiative. In which process technologies are you taping that out? And second question that is related to the previous one, did you compare to BOOM, Berkeley's outvoter machine? Because that is also a high performance core.
Okay.
Thanks.
Yeah, so for 101 chip, the technology node, actually we use 110 nanometer technology. And for each student, actually we have, this is because the cost, this is probably is the most cost effective, efficiency node for us. And for BOOM, I think BOOM is a quite good core. And this is actually is very good for research. But XiangShan actually is industry grade, and there are already some companies are using XiangShan for their products.
Thank you.
So thank you. We're up on the time on this slot. Thank you, Dr. Bauer, for presenting.